Today we're going to do section 4.1, vector spaces and subspaces. Many concepts concerning vectors in Rn can be extended to other mathematical systems. We can think of a vector space in general as a collection of objects that behave as vectors do in Rn. The objects are such a set are called vectors. A vector space is a non-empty set V of objects called vectors, on which are defined two operations called the addition and multiplication by scalars, or real numbers, subject to 10 axioms on the next page. The following axioms must hold for U, V, and W in V for all scalars C and D. The first one, U plus V is in V. This is closure. Second one, U plus V equals V plus U, the commutative property. Number 3, U plus V plus W equals U plus V plus W, the associative property. There is a vector called the zero vector in V such that U plus 0 equals U. This is the identity for addition. For each U in V, there's a vector, negative U in V, satisfying U plus negative U, which equals 0. This is the additive inverse. C times U is in V. This is also shows closure. C times U plus V equals CU plus CV, which is the distributive axiom. C plus D times U equals CU plus DU, which is also distributive. CD times U equals C times DU, which is associative. And 1 times U equals U. It's the identity for scalar multiplication. Let's look at this first example. Let M be a 2 by 2 matrix. A, B, C, D. A, B, C, and D are real. In this context, what is the zero vector? So in this context, the zero vector would just equal 0, 0, 0, 0. That would be your zero vector. Example 2. Let n greater than or equal to 0 be an integer, and Pn equal the set of all polynomials of degree at most n greater than or equal to 0. Members of Pm have the form P of t equals a0 plus a1 times t plus a2 times t squared, all the way to an times t to the n, where a0, a1, and an are real numbers, and t is a real variable. The set Pn is a vector space. Verify axioms 1, 4, and 6 that we just went over. Let P of t equal a0 plus a1 plus t. Let Q of t equal b0 plus b1 plus t, all the way to bn times t to the n, and let C be a scalar. Axiom 1. The polynomial p plus q is defined as follows. So to verify this, p plus q equals p times t plus q times t. Therefore, p plus q equals pt plus qt, which equals a0 plus b0 plus a1 plus b1 times t, all the way to an plus bn times t to the n, which is also a polynomial of degree n. So p plus q is in Pn. Axiom 4. The zero vector equals 0 plus 0t plus 0 all the way to 0t to the n, the zero vector in Tn. So P plus 0 times T equals P of T plus 0 times T, which equals A plus 0 plus A1 plus 0 times T all the way to AN plus 0 times T to the N, which would then equal A0 plus A1T all the way to AN to TN, which equals P of T. So P plus 0 equals the P vector. And axiom 6, C P times T equals CP times T. CA of 0 plus CA1 times T all the way to CAN times T to the N, which is in Pn. The other 7 axioms also hold, so Pn is in a vector space. Subspaces. Vector spaces may be formed from subsets of other vector spaces. These are called subspaces. A subspace of a vector space V is a subset H of V that has 3 properties. The 0 vector of V is in H. For each U in V in H, U plus V is in H. For each U in H and each scalar C, C times U is in H. Let H be A0B, A and B are real. Show that H is in the subspace of R3. So using A, B, and C, we have to show that they're true. So A, the 0 vector, is in H. We're letting A equal 0 and B equal 0. For B, U is A0B. Let V be C0D. U plus V would equal A plus C, 0, B plus D, which is also an H. And then C, U equals A0B. We're letting C be an element of the real numbers. So CU equals CA0, CB, which is in H. So note that in this picture here, vectors A0B and H look and act like points AB and R2. So this point here we're talking about is A0B. So this point right there. Let's look at example 4. Is H x plus 1, where x is real, a subspace of R2? So we're asking, does H satisfy properties A, B, and C? So the first thing that we look at here is, does it have the 0 vector? And the 0 vector, if we look at this, our axiom A would be right here. The 0 vector. So it does not satisfy A. So first, you could say no. There is no 0 vector. Therefore, H is not a subspace of R2. So the property fails. Also, you can show that if we let U equal 0, 1, and V equal 1, 2, then U plus V would equal 1, 3. And U plus V is not in H, so property B fails. And if I were to show that on here, this would be U. U was 0, 1. V was 1, 2. But U plus V was 1, 3. And that clearly is not in H. Theorem 1. If V1 all the way to VP are in the vector space V, then span V1 to VP is a subspace of V. So let's recap. To show that H is a subspace of a vector space, use Theorem 1. To show that a set is not a subspace of a vector space, provide a specific example showing that at least one of the axioms A, B, or C from the definition of a subspace is violated. So let's look at example 5. Is V A plus 2B and 2A minus 3B, where A and B are real, a subspace of R2? Why or why not? So we would have A plus 2B and 2A minus 3B, which we could then write as A and 2A plus 2B minus 3B, which then we can factor out the A and have 1, 2 plus B times 2, negative 3, stating that this is V1, this is V2. So V equals my span, V1, V2. And therefore, V is a subspace of R2. And this comes from Theorem 1. You also could go ahead and see if you can row reduce this to the identity matrix, which you can. So the first thing I can do is I can take negative row 1 and add it to row 2 to get 0, negative 7. And then I could take 1/7 of row 2, or negative 1/7 of row 2. Let's do that. And that would also get rid of the negative there. And then I could take negative 2 times row 2 and add it to row 1, and I would have my identity matrix. Let's look at example 6. Is H A plus 2B, A plus 1, and A, where A and B are real, a subspace of R3? Why or why not? And just looking at this, you can tell that the 0 vector is not part of that. So our answer will be no, because our 0 vector is not part of H. There's no combination of A and B that will result in the 0 vector. Because if A was -1, it would make A plus 1 0, but it wouldn't make this 0 here, nor would it make the top one 0. Example 7. Is the set H of all matrices of the form 2AB, 3A plus B, 3B a subspace of M 2 by 2? Explain. So first, we can take 2AB, 3A plus B, and 3B, and rewrite this as 2A, 3A, 0, 0, plus the matrix 0, B, B, 3B, and then factor out my A and get 2, 0, 3, 0, factor out my B and get 0, 1, 1, 3, and then H equals the span. So therefore, H equals span of 2, 0, 3, 0, 0, 1, 1, 3. And H is a subspace of M2. And so H is a subspace of my M2 by 2 matrix. So matrix, that's a 2 by 2.